Well, the topic of our lesson is basic data types. And let me remind you that when we discuss about machine or computer data type, we define it as three items, where M is a set of values, sigma is a set of operations that can be applied to these values, and S is a storage structure. So the method of representation and processing data in computer, in programming language. And following this definition, we will describe all the data types in C language. We start from numeric data types, because numeric information is one of the important kinds of information, and all the programming languages, any programming language contains the data type that corresponds to numeric data. The data types in C language can be divided into several groups according to the value sets of these numbers. First division is that there are integer valued data types and real valued data types. Integer valued types is divided into unsigned types for non-negative numbers and signed types for negative and positive numbers. And there is one special integer valued type char, that has a dual nature. Its values can be interpreted both as both symbolic and integer, according to the place of where you use this type and the operations that you apply to the variables of the type char. In C program, the integer constants can be written in three forms of numeric notation. Decimal, our usual notation of numbers that we use every day in our life. And also we can use two special forms of notation, so-called octal and hexadecimal. Octal is used very rare, but hexadecimal notation for integer numbers is used rather often. For example, when we work with pointers, we will work with pointers later. All the information related with pointers is represented not in decimal form of notation, but in hexadecimal. And the last comment, the last remark is that integer and real types have several modifications according to the size of the value set, the size of the memory required for the data storage, and so on. Well, of course, this information may be not real very useful for you in writing the programs, but you should understand these fundamentals of storing numbers. And first, I want to say a few words about representation of integer value data in computer memory. Do you know something about binary numbers?
You use for true and false?
Only 1 and 0.
1 and 0, but how to interpret these? How to interpret these notation?
Like true and false, like for bool functions. Like Boolean.
No. It's not Boolean numbers. It's yes, it can be interpreted like Boolean numbers, but also these notation can be interpreted as ordinary number. And I don't want to go into very great details, but just a few remarks about different system of notation. Just a few remarks about different systems of notation. I open another presentation. I will send you these, both of these presentation, both of the slides in the end of the lesson. Well, in our usual life, when we write number, we use so-called positional or radix system of notation. What is this number? 383. We use this short form, just 383. But this short form can be interpreted as 3 times 100 plus 8 times 10 plus 3 times 1. So this is the position of units. This is the position of tens, and this is the position of hundreds. And this number, sorry, I just mute your microphone. This number can be written in also in this form: 3 times 10 power 2 plus 8 times 10 power 1 plus 3 times 10 power 0. 10 power 0 is 1. 10 power 1 is 10. 10 in square is 100. So there is a strong correspondence between the position of the number and the corresponding value. So if this number has position 3, it corresponds to 10 power 2. We start numbering from 0. 0, 1, 2. 0, 1, 2. And each digit corresponds to some power of 10. In decimal, and this system of notation, is called decimal system of notation. And to write a number in this system of notation, we use 10 digits. Let me repeat again that in different countries, these digits called differently. In Russia, we called it arithmetic digits. Maybe in other countries, it has another name. So these digits, and we use the powers of 10. And this 10 is called radix of the system of notation. By the way, why do you know, maybe you know, or maybe you can make some guess, why in our real life we use a decimal system of notation with radix 10? Do you have any ideas why people use a system with radix 10?
To get specific results or to calculate specific numbers less than 1?
This system of notation, of course, is very old. People use this system of notation hundreds of years, and it comes from. So this is one hypothesis about this system of notation, because people have 10 fingers on the 10 fingers, and that's why people use 10 as a radix of notation. In some other world where people have 8 fingers, they will have a system the radix 8. Well, of course, it's just a remark about system of notations, but from mathematical point of view, we can use any integer number as a system, as a radix of the system of notation. And there is a theorem that for any integer number p greater or equals to, and any positive integer number n may be represented in the following form: n equals to beta k times p power k plus beta k minus 1 times p power k plus 1, k minus 1, and so on, up to beta 0 p power 0, where coefficients beta are integer and satisfy their inequalities that beta is between 0 and p minus 1. And the number p is called radix. And we can write the formula 1 in short, reduced form, like n equals to beta k minus 1, and so on, beta 0. If you compare this theoretical statement with this slide, you see the strong correspondence that in decimal system of notation we use 10, right, as p, and we use digits beta for we use digits from 0 to 9 to write this number. And of course, in real life, we never use this expanded form. We use this short form to write numbers. And this form too is called positional representation of the number n in their system of notation with radix p. And from this mathematical theorem follows that we can use any number p to represent the numbers. We can use 10, we can use 5, we can use 4, 11, 12, any number with radix p. But in programming, we consider 3 special classes, 3 special system of notation: binary with radix 2, octal with radix 8, and hexadecimal with radix 16. And of course, we pay attention on binary system of notation with radix 2. If the radix is smaller or equals 10, then all the coefficients are not greater than 9. And it's possible to use usual decimal digits from 0 to p-1 as the digits in radix system in system of notation with radix p. And there is a very simple rule to transform the number from non-decimal system of notation to decimal one. Let's consider these two examples. The number 325 that is written in system of notation with radix 8 octal system. How to transform it into our usual system of notation? First, we should number the digits from right to left, starting from 0. 0, 1, 2. After that, we should write the corresponding formula. 3 times 8 power 2, 2 times 8 power 1, 5 times 8 power 0. 8 is a radix, and 0, 1, 2 are number of digits. And finally, we have 182, 16, and 5. And the final result is 213 in decimal system of notation. And the next example, or I miss one here. Let's consider this number written in binary system of notation. Again, if we use the system of notation with radix 2, we can use only 2 digits, 0 and 1. All the digits must be smaller than this radix. How to convert the binary number into decimal? Again, number the digits starting from 0, 0, 1, 2, 3, 4, and write the formula with corresponding digits and powers of 2. Here the radix is 2, and we use
Oh.
Sarah, you're not talking, by the way, if you can hear me. Oh, never mind. Okay. He deceived.
I thought I got muted. I was like, oh.
Yeah, I think he deceived. Well, that's nice.
So this whole what did he call it? I forgot what it was called already. The system of notation is kind of like the modulus, right?
Yeah, I think, yeah, probably.
Sorry, I have some problems with the internet connection.
Oh, no problem, sir.
Now I restore my connection. Well, if you have any questions about system of notation, you are welcome to.
I was just saying, is this system of notation similar to the modulus, the percentage thing that we did in practice programming? Because we did an assignment to isolate each digit on a number, yeah, and it was using something similar.
The system of notation related with storing the numbers, and to explain how the numbers are stored in computer memory, I should consider the system of notation.
Okay.
Well, let me share the screen again. Well, do you see it?
Yes, sir.
Well, let's continue. We'll stay here. Let me check the recording. Is it? Yes, it's turned on. Now you understand the idea. Well, and after that, I can compute the powers of 2. 1, 2, 4, 8, 16, and write the corresponding number 29 in decimal system of notation. Well, and when people create computers, on first computers, very first computers, people try to use a decimal system of notation, but it's very hard to implement the electronic device that can support decimal numbers. And it's very simple, not very simple, it's more simpler to implement the electronic device to support binary numbers, because a binary number can be stored in a rather simple way. It has just 2 digits, 2 states, 0 and 1, that can be coded rather simple in electronic device. That's why in computer memory, to store the number, we use binary system of notation. Maybe I skip these slides about hexadecimal system of notation, because maybe I come back to these slides when we will consider pointers. Or maybe right now. Okay. The thing that I want to show you, that the one number can be written in different system of notations: binary, octal, hexadecimal. And in computer memory, the numbers are stored in binary system. Well, let me show one example in Visual Studio. This example will related with octal system, because the octal system is more simple than hexadecimal system of notation. Just a very simple example in Visual Studio. Let me declare one number. Let me declare the integer number 10, and let me output this value to the screen. What we see on the screen? Of course, it's very simple. We see a equals to 10. We see a equals to 10. But let me write this number 0 and 10. One remark: when the first digit of the number is 0, this value, this number, will be considered as octal number with radix 8. Who can guess what we will see on the screen now? If this number will be considered as octal number with radix 8. No ideas.
8. I
8.
don't know. Just
Just a guess. Right.
3.
No. 8. We see 8. Let's check. Yes, we see a equals to 8. Of course, let me repeat again that it's just some, maybe you consider it some trick that doesn't correspond to programming, but it explains the system of notations. And please let me, I just reconnect. I use another, because now I connect to very bad connection. Okay, let's fix this connection. This number is considered as not hexadecimal, octal number. When we use octal number, radix 8, how this number is written? Is written 1 times 8 power 1 plus 0 times 8 power 0, according to the positions. Well, let's write another number, for example, 21. How this number will be written in, I write here, octal. 21 with radix 8. 2 times 8 power 1 plus 1 times 8 power 0. It equals 2 times 1, and it equals to 17 in radix 10. Let's check 21. Yes, we see 17. We see 17 on the screen. Well, of course, when you write a program, I think you will never use octal system of notation. but it explains that this is implemented in programming language and it can be used. Well, any questions about it? No questions. Okay. And in computer memory, the numbers are stored in binary system of notation when we use zeros and ones. Unfortunately, binary system is not supported directly like octal system. Binary system.
Your screen is not showing, sir. The screen share is not on.
Screen sharing is not going on.
Yeah, I don't know if you need it, but yeah, just to let you know. Oh no, sorry, I had it minimized. Sorry, that's my fault. I'm sorry.
Okay.
I had it minimized on the corner.
Okay. The question, why does Visual Studio read it that way instead of in 10? Right, very simple. The prefix 0, this first 0 responds to the number. When you write some number, when you write the number like this, of course, this number will be treated as a decimal number. And you see on the screen 2. But if you will the prefix, this number are treated as octal number. And you see on the screen 26, the number system. Okay, and vice versa. let me show this another feature, another trick. You can write here keyword oct, and after that, this number A, will be output to the screen in octal system of notation. Here, 32 is in decimal system of notation, but when I use oct, then will be output to the screen in binary, or sorry, in octal. Is 40. 32 in decimal will correspond to 40 in octal. Please, do you have any other questions?
No.
No. Okay. Well, but again, I think nobody will never use octal system. I show you here as example. In programming, in computer memory, in computer memory is used binary system of notation. The system of notation that use binary digits, 0 and 1. Let's look to this number. Let's look to this number that written in binary system of notation. These first zeros means nothing, and the numbers is significant digits is 101. And this number in binary system will correspond to 5 in decimal system. Let's check it. 101 with radix 2. How to write it? It equals to 1 times 2 power 2 plus 0 times 2 power 1 plus 1 times 2
power
power
0.
0. And if we compute this value, we will have 5 in decimal system of notation. For example, if you add here 1 more 0, 1, 0, so the number is written as 1, 0, 1, 0, 1. What you should write here? We should write 0 times 2 power 3 and 1 times 2 power 4. So we should add here 16 and we get 21 in decimal system of notation. Well, how to store the decimal number? Very simple. We should convert it. We should write it in binary using this form and store in computer memory a sequence of zeros and ones. Well, of course, the exact implementation is quite complicated. It's just a general idea of representation of numbers in computer memory, but this idea is explains everything. We take decimal number, we convert it into a binary system, we write the representation of this number, and we write it in computer memory cell. If the number is shown, we add first zeros to its notation. Do you understand the main idea of representation of integer numbers?
Yes.
You have no questions. Okay. Well, I have a question to you. Suppose that we consider the 1 byte, we consider 1 byte cell, 8 bits, 8 binary digits. What is the largest number in binary system that we can write, that we can store in 1 byte? What is the largest number? Of course, this question from the first point of view is rather hard. Let's consider more simple question. Let's consider just 3 cells, for example. Let's consider 3 binary digits, 3 cells. What is the largest number?
111.
Yes, sure. 111. Use 3 cells. The largest number is 111. But what is the decimal value of this number? Let's quickly compute.
111. It's 6 plus 8. It's 12.
No. What's
14.
8? No. So we have 0, 1, 2. 1 times 2 power 2 plus 1 times 2 power 1 plus 1 times 2 power 0. What number we have?
Okay. 21.
7.
7. Excellent. We have 7. Okay. Let's consider 4 cells. What is the largest number that we can write in 4 binary digits? Of course, in binary.
4-1.
Yes.
1-1-1.
In binary system, the answer is very simple. 1, 1, 1, 1, right? In binary.
Yes.
But what is the corresponding number in decimal? We should take this value and add one more
Plus
number.
1
2
to
power
3.
3, right? And what is the number? What we have? We should add 7 plus 2 power 3.
8,
15.
7 plus 8. 15.
15, right? 15. Right. The next example, 5 cells. What is the largest number? 5 ones. We should take the number and power 4.
4, yes. 15 plus 16.
Plus 16.
31.
Right.
I think 31.
31. So, did you guess about the rule? What is the rule? What is the largest number that we can write in 8 cells? 1, 2, 3, 4, 5, 6, 7, 8.
8.
How to write?
1 times 2 to the power
31
7.
plus
Okay.
15.
What is the rule? What is the rule? How to count
5, 1, 1. Yes, plus up 4, 1.
Without computing of this very long sequence of powers of 2. The rule is very simple. Let me write the correct answer. This 7 in decimal, it can be written as, well, here we have 3 binary digits, so it's 2 power 3 minus 1. Here we have 4 binary digits, and it equals to 2 power 4 minus 1. And here we have 5 binary digits. It equals the large 2 power 5 minus 1, right? Here we have minus 1, 32 minus 1, and when we have 1 cell with 8, we have 2 power 8 minus 1. Right? And if you briefly compute the value of 2 power 8, what is 2 power 8? It means that the largest number, the largest integer number that we can write in 1 byte cell is 2 power 8 minus 1.
Yeah.
Well, I hear my echo. I just please turn off your microphones. Well, and it explains maybe one of the most important things, the range of representation of numbers. if we use binary numbers for storing, that in this case we can represent integer number in some specific range. Suppose that their numbers are between, so the numbers are positive, and we use a 1 byte cell. In this case, any number, any integer number is in the range from 0 to 255. The range of representation is from 0 to 255. Suppose that we use 2 for representing the integer 16 ones, 1, 1, 1, and so on, 16 ones in binary. It's hard to compute in mind this number, but the formula is very simple. 2 power 16 minus 1, right? And in this case, binary number in the range from 0 to power 16 minus 1. This number, maybe it's written here in my presentation. Yes. Well, before we consider the next slides, a few words about representation of negative numbers. Again, I don't want to go into details, but just to explain you the main idea. When we represent positive numbers, suppose all the numbers are positive, non-negative, then the largest number is 1, 1, 1, 1, 1, all ones. And the range of representation is between 0 and 255. Both the numbers can be positive and can be negative too.
We
In
use
this case,
long.
no, no, I explain you the idea of storing.
Okay.
If we consider eight computer cells in 1 byte, this first cell in this case will be considered as sign. For example, if sign is 0, the number considered as positive. If sign is 1, the number considered as negative. Idea is very simple. That's the first cell, and if this cell is, the cells will be treated as positive. This cell is 1. These cells will be considered as negative number. But in this case, how many cells for number we have? We have 8 minus 1 cells, because 1 cell we take for the sign. And in this case, when we consider their range, it will be from 2 power 7 with minus up to 2 power 7 minus 1. Well, do you understand the idea, right? Take one
Yes.
bit for sign, consider now the bits as an absolute value. 2 power 7 is 128. So the range of representation of 1 byte numbers, positive and negative, is plus minus 127. And the same situation is for all the numbers. When we consider the positive and negative numbers, we select one cell, one bit, and if this bit is 0, the number is considered as positive. If the bit is 1, the number is considered as negative. So the range will be 2 power 15 minus 1 minus 2 power 15. Well, the same is written. Yes, the first cell is only for the sign. And here is explanation how to store the negative number in complement onto code. I skip it. So I explain the idea. And all of these numbers can be used in C language. All of these numbers. For example, the smallest integer number is the 1 byte integer number, 1 byte integer number, and the range is from 0 up to 255. Signed char or just char, the range of representation is from minus 128. Sorry, I mute your microphones because of some sound. Well, the next type is unsigned short int and signed short int. For these numbers, we use 2 bytes for storing. That's why for unsigned short int, the first number is the largest number is 2 power 16. It's written here. 65,535. The values of signed short int is from minus 32,000. And of course, the most used type is just int. Is just int, and it can be when you write just int, it's assumed that this value is signed. If you write int with prefix unsigned, it means that we consider the number without sign only a positive number. And on modern computers with 32 architecture or even 64-bit architecture in programming languages, int has a range unsigned int has a range from 0 up to 232, 2 in the power 32 minus 1. I compute this number. This is the number 2 power 32 minus 1. This is the largest number that can be represented in the int type. And when you use signed int or just int, the range is from this number to this number. 2 power 41 minus 1. Let's check it. Check it in Visual Studio. Let me declare integer variable a, and let's assign this number, or even this minus 1. I subtract 1 just to show you. When I add 1, I output to the screen a plus 1. What number I should see on the screen? This one. 2, 4, 7, 8, 3, 6, and so on. Because here I subtract 1 and I add 1. Okay, let's check it. Yes. See the number, but let's output a plus 2. A plus 2 means, or even let me delete this minus 1 and output a plus 1. Let's run this program. And we see very, very strange result that this very large positive number plus 1 equals to negative number. This situation is called overflow. When the number exceeds the upper bound of the numbers. This is the upper bound for the integer numbers.
Is there no lower bound?
Yes, sure. The lower bound is also no. It's written here. This is the lower bound. This is the lower bound. Let's check again. This is the lower bound. And if you, for example, add 1 to the lower bound, so you still be inside the range, you see correct result. Minus 214 and so on, and the last digit is 7. But if you subtract 1 to the lower bound, you'll see positive number. The same situation. If you subtract 1 to the lower bound, you will see the very large positive number. Well,
okay.
Of course, well, the main point that you must remember that int type has a fixed range of representation with upper bound and lower bound. Within this range, all their operations will be carried out correctly. But if your number exceeds the range, the result can be unpredictable. Again, let me assign again the upper bound. This is the upper bound. And let me write a plus 2. It's negative. A plus 3. Negative. I don't remember where, but in some cases we will have some just a positive number, maybe 8 times something. Yes. The result can be completely unpredictable. You take very large number, you can apply multiplication 8 times 4, and you get some strange result. This situation again is called overflow, and sometimes it happens in programs. This constant, as I or maximum, I don't remember. Yeah, max. So you can use in max as the largest value with that. So instead of this constant, you can use just a predefined constant int max for the upper bound of the integer numbers, and for the lower bound you can use int min. Well, any questions?
No.
No. Okay. Let's come back to the presentation. So, and finally, the most powerful integer type is a long int. But unfortunately, even in modern computers, in modern operating system, long int and int are completely the same. Long int will be was used as different type on rather old computers in 16-bit architecture. But today, long int and int are the same. If you want to extend the range of representation of int, you can use some special types, like, I don't remember how it's written, maybe 64 with such prefix, yes. Int 64 with this prefix is a number that uses 8 bytes for. It has very, very large range of representation, 2 power 64. But the usual type int has a 2 power 32. It's also enough for representing, for using in the most cases. Well, okay. I also shows you the question. Signed int max. Yes, you can use another. You can use another constant. And the general form of notation of integer is following. plus minus, then some prefix, then the number, and after that some suffix. Plus minus denotes the sign. Prefix and suffix are optional, and D are digits. And also, I already show you that 0 says that the number is octal, and the digits must be from 0 to 7. And it may be another prefix, 0x, in the case when the number is hexadecimal. But maybe we consider it later when we will have enough time for it. And sometimes we can use suffix. Suffix characterize the type of the number. For example, suffixes L are used for declaration of the constant of the long int, H for short int, U for unsigned int. For example, any combination LU corresponds to the type unsigned long. Any combination of HU corresponds to the type unsigned short. For example, you can write something like this. Short int C equals to 5 sorry. Maybe doesn't work in this compiler. Long C equals to 5L. It means that this constant 5 will correspond to the type long. Or LU, it means unsigned. Unsigned long. Okay, but again, I repeat that these suffixes are used not very often, and in the most cases, in 99.9% of the cases, we'll use this form of notation for integer numbers. Well, so we consider these the integer numbers in details. Now I think you understand how the data in integer types are stored. You understand about you know the range of representation of the integer numbers. Well, do you have any questions about it? Please, you are welcome. We have time for the questions.
How do calculators calculate numbers larger than the maximum integer when we have a maximum integer on integer type?
No, okay. When you write your using C compiler, you can use only this int. When you calculate this number, calculator uses some special data types for working with their integer numbers.
Oh, so
Well,
the data types they use don't have an upper limit?
Well, I repeat again that this type, int, is so-called basic type or built-in type. And you use, when you should extend the range of representation of a number, you should define your own type. You should implement the operations with this type. And there are some software libraries that can operate with very, very, very large integer numbers, very, very large real numbers. But it's not a built-in types. It's a user-defined type.
Okay. All right.
Well, questions? If you have a well, we have 10 minutes, and maybe I don't want to start to. I don't want to discuss about real data types. Maybe I just say a few words about operations with integer numbers. Of course, it's a topic of the next lesson, operations, but just a few words about operations right now. Of course, you can use some obvious operations with integer numbers like addition, subtraction, multiplication, and so on. For example, C equals to A plus B. Let's assign some good numbers like 2 and 3, and let's output C on the screen. Of course, operation plus is correspond to the addition of two integer numbers. Star corresponds to multiplication. 2 times 3 either and if you change the order of operands, the result will be the same. But what happens if you apply division for integer numbers? 2 over 3. What is the result of this operation for integer numbers?
Going to be a long decimal. But 0.666.
I answer the question in chat later. A over B, what is the result? In mathematics, when we apply the division, we have 2 over 3 like number. The result is 0. It's a division with remainder, so-called integer division. 2 over 3 division, we have 0. If A equals to 1, we also have 0. If A equals 4, what is 4 over 3? What is the result? the integer part of the result. Here, integer division can be interpreted as integer part of the result. What we have as integer part of the result?
1.
1, right? The result is 1. And 5 over 3 is also result 1. And so on. It's integer division. And there is a special operation that denoted as a % sign. % sign is operation of getting the remainder. 5 over 3. What is the remainder of this operation? The integer part.
The decimal.
No. So 5. You should represent this when you divide 5 equals to 3 times 1 plus 2. You should represent this number in this form. 1 is integer part of the division, and the remainder is 2. C equals 2. % sign is operation getting the remainder. For example, 10 times 3. Sorry, 10 over 3. 10 getting the remainder 3. How to? 10 is 3 times 3 plus 1. The remainder is 1. And the integer of the division is 3. Do you have any questions about this operation? This is a 2 special operations that we don't use it in our life very often, but in programming, integer division and getting the remainder is used rather often.
The percentage sign is not called module, it's called remainder.
Oh, okay, you can call it module. Of course, you can call it module. You can, in mathematics, it's called a remainder. In here, you can call module.
Okay.
Well, we come back to the operations with the integer and real numbers on the next lecture. So we start with detailed consideration of the real numbers. And after that, we consider operations with integer numbers and real numbers. And there is one question in chat. What is the difference between constant and literal constant? Okay, when I say constant or named constant, it means declaration const. For example, d equals 10. Here I declare a constant with name, but also I can use the constant in the expression. In this case, this constant is unnamed constant or literal. This is a constant without name, without specific name. Well, the time of our lesson is over for today. Do you have any questions about integer numbers in C language?
There was a question on the chat earlier.
But I answer all of these questions.
Oh,
Yeah.
okay.
I answer these questions. Well, if you don't have any questions, let me finish our recording, stop recording.